At the beginning of the universe, there are no atoms at all, no hydrogen, no oxygen, no stars, oceans, stones, or living cells, only heat, radiation, and particles moving through a cosmos too violent for matter to hold together. And yet, from that chaos, the atom eventually appears a tiny structure balanced between powerful forces, quantum uncertainty, and the slow cooling of space itself. Its existence seems ordinary now, but even a slight change in the laws of physics could have erased atoms, chemistry, planets, and life before they ever began. Viewers who enjoy calm journeys into the deepest questions of science are warmly invited to like, subscribe, and share this film with someone drawn to cosmic mysteries. Thank you for spending this time here. A comment with the local time and viewing location would be a wonderful way to mark where this journey begins. Now, the story can move back to the atomless universe and follow the long path toward everything that exists. Every stone, cloud, ocean, tree, planet, and living cell shares a hidden architecture so common that it almost disappears from thought. Matter seems solid, continuous, and immediate. A hand rests on a table and meets resistance, yet none of these things is truly continuous. Beneath every surface lies a vast population of atoms, tiny structures repeated in numbers beyond ordinary imagination. They assemble into minerals, gases, metals, oceans, bones, blood, and stars. They differ in arrangement, energy, and composition, but the same basic pattern returns everywhere visible matter appears. At the center of each atom sits a compact nucleus, built from protons and usually neutrons. Around it spreads the quantum presence of electrons, not as miniature planets following neat tracks, but as shifting regions of probability. The atom is not a small hard bead. It is a stable relationship between particles, forces, and quantum rules. Almost all of its volume is open space. Yet that space is filled with fields, possible locations, and the invisible structure of physical law. The solidity of matter emerges from interactions rather than from tiny pieces packed tightly together. Electrons in neighboring atoms resist being forced into the same quantum states. The floor does not yield because atoms in the floor and atoms in a body cannot simply pass through one another. Solidity is a consequence of rules acting across distances far smaller than any eye can resolve. This alone makes the ordinary world strange. Everything feels direct and substantial, yet everything rests on invisible patterns. The atom is so successful that it becomes easy to regard it as inevitable, as though any universe containing matter must naturally produce atoms. But that conclusion arrives too quickly. Atoms are not the simplest possible form of matter, nor are they guaranteed by the existence of particles. They require several conditions to be satisfied at once. There must be positively charged nuclei and negatively charged electrons. The attractive force between them must be strong enough to create bound structures, but not so strong that electrons collapse into the nucleus. Quantum mechanics must provide stable energy levels. Protons must survive. Neutrons must have the right mass to help build larger nuclei without turning all matter into a different form. The strong nuclear force must bind some combinations of protons and neutrons while refusing to bind others too easily. If these balances shifted in certain directions, atoms could become unstable, rare, or impossible. A universe could contain energy and particles without chemistry. It could expand, cool, and remain forever without worlds, oceans, or living cells. The presence of atoms therefore raises a question deeper than their structure. Why does matter organize itself this way at all? The answer begins with history. Atoms do not appear at the first instant of the universe. The early cosmos is far too hot and dense for them. Particles collide with such violence that fragile structures cannot endure. Quarks, electrons, neutrinos, photons, and other ingredients move through a universe still changing with extraordinary speed. Even protons and neutrons cannot exist immediately. The conditions must first cool enough for quarks to bind. Later, protons and neutrons gather into the first atomic nuclei. Much later still, electrons settle into stable relationships with those nuclei. The atom is therefore not the starting point of matter. It is an achievement of cosmic cooling. It emerges only after the universe has expanded enough for structure to survive. Everything familiar is made of atoms not because atoms are the most basic things in existence, but because the universe passes through a narrow sequence of conditions in which atoms become possible, stable, and abundant. Their success depends on both the laws of physics and the particular history of cosmic expansion. Once formed, atoms gain an extraordinary advantage. They endure. A hydrogen atom may travel through space for immense spans of time without changing its identity. It may drift through a dark interstellar cloud, fall into a young star, become ionized in stellar heat, escape in a stellar wind, cool again, join a molecule, enter a planet, and later become part of an ocean or a living organism. This persistence allows matter to carry structure through time. Nuclei support atoms, atoms support molecules, molecules support solids, liquids, atmospheres, and chemistry. Chemistry supports metabolism, heredity, and the intricate organization of life. If atoms lasted only for brief moments, complexity would collapse before it could grow. Their durability gives the cosmos a kind of memory. Matter can preserve arrangements long enough for new arrangements to form. Yet even the simplest atom contains a profound mismatch between appearance and reality. Hydrogen, the most abundant element, consists of one proton and one electron. In a simple picture, the electron circles the proton like a moon around a planet. That image is useful at first, but nature is less familiar. The electron does not follow a single hidden path waiting to be discovered. Its behavior is described by a quantum state, a spread of probabilities that determines where it may be found. The atom has a definite structure, but not one that resembles a miniature solar system. Its stability comes from quantized energy levels, meaning the electron can occupy only certain allowed states. It cannot slowly spiral inward while radiating away energy in the manner predicted by older classical physics. The lowest energy state forms a limit. There is nowhere lower for the electron to fall while remaining bound to that nucleus. Quantum law prevents the collapse that ordinary intuition seems to demand. The atom survives because the microscopic world does not obey the rules of everyday motion. This stability reveals that the visible world depends on a hidden domain where probability, fields, and discrete energy govern events. A glass of water appears calm, but within it atoms and molecules move continuously. A metal bar appears uniform, but its electrons occupy collective quantum states across a crystal lattice. A breath of air seems nearly weightless, but it contains an immense number of molecules colliding in all directions. Still, atoms alone do not make everything. Light is not made of atoms. Dark matter, whatever its final nature proves to be, is not known to consist of ordinary atoms. Neutron stars contain matter crushed beyond ordinary atomic structure. Even within the visible cosmos, atoms represent only one form among several kinds of physical existence. The claim that everything is made of atoms is therefore both profoundly true and carefully limited. Nearly every ordinary object, every landscape, every organism, and every planet is atomic. But the universe as a whole contains more than atomic matter. Atoms dominate the world that can form complex structures, reflect light, undergo chemistry, and become familiar. They are not all that exists, but they are the main framework through which the cosmos becomes textured and visible. Why do these particular structures occupy such a central role? Why do protons and electrons form stable unions? Why do nuclei come in a range of types instead of only one? Why can atoms link together in countless arrangements while preserving enough order for complex matter to endure? The answer lies partly in electromagnetism, partly in the strong nuclear force, partly in quantum mechanics, and partly in the cooling history of the universe. No single ingredient is sufficient. Atoms arise from cooperation among laws that operate at different scales. Gravity shapes galaxies and stars but has almost no direct control over atomic structure. The strong force binds the nucleus but fades rapidly outside it. Electromagnetism binds electrons to nuclei and atoms to one another. Quantum mechanics determines the allowed states that keep the whole structure from collapsing. Together they create a form of matter that is stable without being inert, orderly without being rigid, and durable without being unchangeable. That balance is the foundation of chemistry. Before there are atoms, there can be no ordinary molecules. Before molecules, there can be no minerals, oceans, atmospheres, or cells. The existence of atoms marks the moment when the universe gains the ability to build lasting complexity from simple parts. Their formation turns a hot sea of particles into a cosmos capable of structure. But this transformation does not happen immediately, and it does not happen easily. To understand why nearly everything familiar is made of atoms, the story must move backward into a time when no atom has yet formed, when light cannot travel freely, and when matter itself is still being assembled from more fundamental pieces. There, in the first moments of cosmic history, the apparent inevitability of the atom begins to dissolve. Before the first atom exists, the universe is not empty. It is crowded beyond ordinary comparison, filled with energy, radiation, and particles moving through conditions so extreme that no familiar structure can survive. Space itself is expanding, but at first the expansion has not yet created enough room or enough cooling for matter to settle into lasting forms. Any fragile arrangement is broken apart almost as soon as it appears. The ingredients of atoms may begin to emerge, yet the atom itself remains impossible. Light is everywhere, but it cannot travel freely. Matter and radiation collide so often that the cosmos behaves like a glowing, opaque fluid. The universe is not a collection of objects floating through space. It is a hot physical medium in which objects have not yet taken shape. At such temperatures, energy does not remain separate from matter in the way everyday experience suggests. Energy can transform into particles, and particles can meet their antimatter partners and return to radiation. The famous relation between mass and energy is not merely an abstract principle here. It governs the population of the young cosmos. When the available energy is high enough, new particle pairs can appear. When particles and antiparticles collide, they can vanish into photons. Creation and destruction unfold continuously, and the universe carries far more motion than structure. This restless exchange does not mean that anything can happen without limits. Conservation laws still govern every transformation. Electric charge is balanced. Energy and momentum are preserved. Quantum rules constrain which particles can appear and how they interact. The early universe is chaotic in appearance, but it is not lawless. The laws are already present, even though the stable forms they will later support have not yet emerged. Among the particles that matter most for atoms are quarks and electrons. Electrons are fundamental particles, with no known internal structure. Quarks are also fundamental, but they do not remain isolated under ordinary conditions. They carry a kind of charge associated with the strong nuclear force, and that force eventually confines them inside larger particles such as protons and neutrons. At first, however, the universe is too energetic for this confinement to create stable composite particles. Quarks move through an intensely hot mixture alongside gluons, the carriers of the strong force. This state is often called a quark-gluon plasma. It resembles no ordinary gas or liquid. The components interact constantly, and the identities of future protons and neutrons are not yet fixed. The raw material is present, but the architecture is not. As expansion continues, the temperature falls. Cooling is not an external process, because there is no colder surrounding space into which the universe releases heat. The cooling happens because the universe itself grows. Radiation stretches with expanding space, and the average energy of particles declines. This gradual reduction in energy changes what kinds of structures can survive. A universe that is too hot for protons can become cool enough for them. A universe too hot for nuclei can later permit them. A universe too hot for atoms can eventually allow electrons to remain bound. Each stage opens only when expansion lowers the energy of collisions beneath a critical threshold. Structure therefore appears in a sequence, not all at once. One of the first major transitions occurs when quarks become confined. As the universe cools to around trillions of degrees, the strong interaction no longer permits quarks to roam through the plasma as freely as before. They bind into composite particles called hadrons. Protons and neutrons are the most important hadrons for the later history of ordinary matter. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Inside each proton and neutron, gluons carry the strong interaction, while temporary quark and antiquark pairs appear and disappear within the quantum fields. Most of the mass of a proton does not come directly from the rest masses of its 3 main quarks. It arises from the energy stored in the strong interaction, and from the ceaseless activity of the fields inside. The building blocks of atoms are already structures made largely from confined energy. Even matter at its most familiar begins as a dynamic arrangement rather than a collection of rigid pieces. Protons are stable, at least on timescales far longer than the current age of the universe. Neutrons are different. A free neutron is slightly heavier than a proton, and outside an atomic nucleus it tends to decay into a proton, an electron, and a nearly massless particle called an antineutrino. This difference matters greatly. It shapes how many neutrons remain available when the first nuclei begin to form. In the earliest moments, protons and neutrons can transform into one another through the weak nuclear interaction. As the universe cools, these reactions become less frequent, and the ratio between protons and neutrons begins to settle. More protons survive than neutrons. This imbalance later determines why hydrogen becomes the most abundant element and why helium forms in a smaller but still substantial amount. Yet even after protons and neutrons appear, atoms remain distant. An atom requires a nucleus and bound electrons. Collisions are too energetic. Photons strike any emerging bound state with enough force to tear it apart. A proton may attract an electron through electromagnetism, but attraction alone is not enough. The surrounding radiation immediately supplies the energy needed to separate them again. Matter exists as a plasma, a mixture of charged particles moving independently. The universe is electrically neutral overall, but it is not locally organized into neutral atoms. Positive and negative charges are present, though they remain unbound. The absence of atoms changes the behavior of light. Free electrons interact strongly with photons. A photon may travel only a short distance before scattering from an electron and changing direction. It then encounters another charged particle, and another. Light cannot cross the universe in a straight, uninterrupted path. The cosmos is opaque, not because it lacks light, but because it contains too much interaction. Radiation is trapped in the same dense medium that it helps sustain. The early universe therefore glows everywhere while revealing nothing across great distances. It has brightness without transparency. This condition continues for hundreds of thousands of years, even though the most violent early stages pass quickly. During that long interval, the universe expands from a tiny, intensely hot state into a far larger plasma. Its temperature falls, but not yet enough for complete atoms. The nuclei and electrons remain separated. Sound waves move through this cosmic medium as gravity compresses some regions, and radiation pressure pushes them outward again. These oscillations leave patterns that will later be preserved in the distribution of galaxies. Long before stars exist, the seeds of cosmic structure are already moving through the plasma. Slight variations in density provide the first unevenness from which later complexity grows. Some regions contain a little more matter than others. Gravity begins to favor those denser regions, though radiation resists rapid collapse. The contest between attraction and pressure creates ripples across the young universe. It is a formative age in which particles gain stability. Forces separate into their later roles. Nuclei begin to become possible, and density patterns emerge. Every later object depends on these early transitions. The hydrogen in stars, the carbon in living tissue, and the oxygen in oceans all trace their ancestry to a time when no atom exists. Matter must first pass through a phase in which it is less organized, more energetic, and more closely tied to radiation. Only after the universe cools through each threshold can the next layer of structure appear. The question of why everything familiar is made of atoms begins here, in the recognition that atoms are not present by default. They require a universe that changes. Expansion must reduce the violence of collisions. Quarks must become confined. Protons and neutrons must survive in the right proportions. Radiation must lose enough energy for bound states to endure. The laws of physics provide the possibilities, but cosmic history determines when these possibilities can become real. The first atom waits within this sequence like a structure that the universe can build only after preparing every part. Before that moment, existence is bright, dense, and restless, full of ingredients that cannot yet hold together. The atomless universe is not a failed version of the cosmos. It is the necessary beginning of the one that follows. Light dominates the young universe, but light is not passive. In the extreme conditions after the beginning, radiation carries enough energy to create matter. The boundary between the two is not absolute. Mass can become energy, and energy can become mass, provided the laws of conservation are satisfied. This exchange is one of the deepest reasons atoms are possible. The ingredients of matter do not need to be present as permanent objects from the first instant. They can emerge from the energy filling the cosmos. This transformation does not resemble a flame hardening into ash or vapor condensing into droplets. It occurs through quantum fields whose excitations appear as particles. In modern physics, particles are not independent specks placed into an empty background. They are localized expressions of fields extending throughout space. The electron field, quark fields, electromagnetic field, and other fields are already part of the universe's physical structure. When enough energy gathers in the right way, those fields can produce detectable particles. Matter emerges not from nothing, but from energy acting through laws already woven into reality. In the early universe, photons collide with such violence that some encounters produce pairs of particles and antiparticles. An electron may appear with a positron, its antimatter partner. A quark may appear with an antiquark. For a brief period, creation and annihilation remain nearly balanced. Matter forms from radiation, then meets antimatter and returns to radiation again. The universe behaves less like a warehouse of fixed objects and more like a shifting balance among fields, particles, and energy. What matters for the later existence of atoms is that the balance does not end perfectly. If every particle of matter had found an antimatter partner, almost all ordinary matter would have vanished into photons. No protons would remain to become nuclei. No electrons would remain to bind around them. The visible universe depends on a tiny excess of matter over antimatter, a difference so small that it is easy to overlook and so important that everything familiar follows from it. For roughly every enormous population of matter and antimatter particles, a slight surplus of matter survives. The exact origin of this imbalance remains one of the unresolved problems of physics. Known interactions contain forms of asymmetry, but the amount observed so far does not fully explain why the cosmos contains so much matter today. The universe made from atoms therefore begins with a mystery before atoms exist. Matter survives because the early balance is not exact. As the universe expands and cools, particle creation becomes harder, photons lose energy, and many can no longer create heavy particle pairs. Matter and antimatter continue to annihilate, but the small surplus of matter has no matching antimatter left to destroy it. What remains includes electrons and quarks, the essential ingredients of ordinary atomic matter. Electrons belong to a family of particles called leptons. They carry negative electric charge and, as far as experiments reveal, have no internal structure. Their simplicity is deceptive. An electron behaves as both a particle and a quantum wave. It can be detected at a particular place, yet between interactions its state spreads through space as a range of possibilities. Later, this quantum nature allows electrons to form the extended clouds that define the size and chemical behavior of atoms. Before atoms form, however, electrons move freely through the hot plasma. They scatter light, exchange energy, and help keep the early universe opaque. Quarks follow a different path. They carry electric charge, but they also carry color charge, the property acted upon by the strong nuclear force. Color charge is not ordinary color. It is a name for a quantum feature that determines how quarks and gluons interact. Gluons transmit the strong force, and unlike photons, which do not carry electric charge, gluons themselves carry color charge. This allows gluons to interact with one another, making the strong force unusually complex, at extremely high temperatures. Quarks and gluons move in a dense plasma. As the temperature falls, the character of the strong interaction changes. Quarks become confined into larger particles. They do not simply drift apart and remain isolated. The force between them does not fade in the same way that gravity or electromagnetism weakens with distance. Pulling quarks apart stores more energy in the strong field. Before a quark can be removed as a free particle, that energy tends to create a new quark and antiquark pair. The result is not an isolated quark, but new composite particles. Confinement locks quarks into hadrons, including protons and neutrons. This transition is one of the universe's first great acts of construction. The most important combinations for atoms involve up quarks and down quarks. 2 up quarks and 1 down quark form a proton. 1 up quark and 2 down quarks form a neutron. The arithmetic seems simple, yet neither particle is a quiet container. Inside, gluons are constantly exchanged. Quark and antiquark pairs briefly arise from the energy of the fields. The proton's mass comes mostly not from adding the small rest masses of its 3 main quarks, but from the energy of their motion and the strong interaction that confines them. A proton is therefore a stable object made from ceaseless internal activity. It keeps its identity not because its interior is static, but because the quantum pattern remains bound. This distinction reaches to the heart of matter. The universe builds durable things from restless processes. Stability does not require stillness. It requires a structure that preserves itself through change. Protons become especially important because they are electrically positive and remarkably long-lived. No proton decay has ever been observed, and if protons do decay, their average lifetime must be vastly longer than the present age of the universe. This endurance allows hydrogen nuclei to survive across cosmic time. Neutrons are only slightly heavier than protons, but that slight difference changes their fate. A free neutron eventually decays, while a neutron bound inside a suitable nucleus may remain stable. The mass difference between the two particles is small enough to permit a rich nuclear world, yet large enough to make isolated protons more persistent. If the relationship were substantially different, the inventory of matter could change radically. The first durable ingredients of atoms are therefore not merely produced. They appear with masses, charges, and interaction strength that allow some to endure while others transform. During the earliest seconds, the weak nuclear interaction continues to convert protons into neutrons and neutrons into protons. As cooling proceeds, these reactions become too slow to maintain balance. The neutron population begins to fall because free neutrons decay, while protons remain. By the time nuclei can form, protons outnumber neutrons. This is why the later universe becomes dominated by hydrogen. A hydrogen nucleus is simply a proton. It requires no neutron and no further nuclear assembly. Every surviving proton is already a potential hydrogen atom, waiting only for an electron and sufficiently cool conditions. The electron and proton carry equal and opposite electric charges. This symmetry allows them to combine into an electrically neutral structure, yet their masses are extremely unequal. The proton is almost 2,000 times heavier, so the center of mass lies close to the proton, while the electron's quantum state extends far beyond it. This difference helps give atoms their scale. The nucleus contains nearly all the mass, while the electron cloud determines nearly all the volume. Matter is therefore built with weight concentrated in tiny centers and size created by much lighter quantum particles. Nothing in ordinary experience suggests such an arrangement, yet it repeats through every atom. At this stage, however, the universe still does not possess atoms. It possesses the parts. Protons move among electrons, photons, neutrinos, and other particles. The positive and negative charges balance across large regions, but they have not settled into neutral pairs. Radiation remains energetic enough to break apart any early attempts at binding. The cosmos has crossed one threshold but not the next. Energy has become matter. Quarks have become protons and neutrons. A small excess of matter has survived annihilation. Electrons remain abundant. The ingredients now exist in stable enough forms to persist. The universe has moved from pure possibility toward architecture, but the walls have not yet risen. Before electrons can settle around nuclei, the nuclei themselves must first be built. Protons and neutrons must find the narrow conditions in which the strong force can join them without the heat immediately tearing them apart. That window will open briefly, only minutes after the beginning, and in that short interval the first elemental pattern of the cosmos will be set. At the center of every hydrogen atom sits a proton, a particle so familiar that it often appears simple. It carries one positive electric charge. It provides nearly all the mass of the atom. It can survive for times far longer than the current age of the universe. In diagrams, it is often drawn as a small coloured sphere resting inside the nucleus, quiet and compact. Yet the real proton is one of the most intricate stable structures known in physics. Its surface is not a shell, its interior is not empty, and its contents do not remain still. A proton is a storm held together by the strongest force in nature, a quantum system in which particles, fields, and energy continually rearrange themselves while the whole object preserves the same identity. The simplest description says that a proton contains 2 up quarks and 1 down quark. These are called valence quarks because they determine the proton's electric charge and several of its most important properties. Each up quark carries a positive fraction of electric charge, while the down quark carries a negative fraction. Added together, they produce exactly 1 unit of positive charge. That neat accounting is correct, but it does not reveal what occupies most of the proton's energy or what gives it most of its mass. The 3 valence quarks contribute only a small portion of the total. The rest comes mainly from their motion and from the energy stored in the strong interaction that confines them. In this sense, the proton is made less from the weight of its ingredients than from the energy of the bond that prevents those ingredients from escaping. The force responsible is described by quantum chromodynamics, the theory of quarks and gluons. The name refers to color charge, a quantum property unrelated to visible color. Quarks carry color charge, and gluons carry it as well. This makes the strong interaction unlike electromagnetism. Photons, the carriers of the electromagnetic force, do not carry electric charge and therefore do not directly interact with one another under ordinary conditions. Gluons do carry the charge of the force they transmit, so they can interact among themselves. The result is a dense web of self-interacting fields inside every proton. A quark emits a gluon, another quark absorbs it, and the gluons can exchange energy with still more gluons. Even in the proton's lowest energy state, quantum fields fluctuate. The interior remains active because complete stillness is not allowed. Confinement gives this activity its boundaries. When quarks are pulled apart, the strong interaction does not weaken in the familiar way that gravity or electric attraction weakens with distance. Instead, the energy stored between the quarks increases. The connection behaves somewhat like a stretched band, though the comparison is incomplete because the strong field is a quantum structure rather than a material thread. If enough energy is added, the field does not release a lone quark. It creates a new quark and antiquark pair. The original quark joins one of the new particles, and the remaining particles form another composite object. Nature produces new hadrons instead of permitting isolated quarks to escape. Every attempt to separate the proton's ingredients therefore changes the system being examined. The quarks remain confined not by an ordinary wall, but by a force that converts separation energy into more matter. Within this confined region, gluons sometimes carry enough energy to produce temporary quark and antiquark pairs. These are often called C-quarks. They appear and disappear as part of the continuous quantum activity inside the proton. The word temporary does not mean unreal. Their effects can be measured, and they contribute to the proton's internal structure. Yet they do not remain as permanent constituents in the same way as the 3 valence quarks, at any moment. The proton contains a fluctuating sea of gluons and quark pairs surrounding the valence pattern that defines its lasting identity. Up quarks and down quarks are most common, but heavier varieties may briefly participate when the quantum conditions allow it. The proton is therefore not a container holding exactly 3 unmoving objects. It is a stable average emerging from countless internal events. This restless interior explains why measuring the proton is difficult. Different experiments probe different aspects of it. High-energy collisions can reveal how momentum is distributed among quarks and gluons. Scattering experiments can map electric charge and magnetism. Other measurements test the proton's size, spin, and response to external fields. The deeper the probe reaches, the more complicated the picture becomes. A low-energy experiment may treat the proton as a single particle. At higher energies, its internal quarks and gluons become visible through their effects. At still higher energies, the apparent number of constituents increases because more of the quantum sea can participate. The proton does not change its identity, but the level of detail revealed depends on how sharply it's examined. Even its spin contains a mystery. Spin is an intrinsic quantum property that behaves in some ways like angular momentum, though the proton is not simply a tiny ball rotating in space. The spins of the three valence quarks account for only part of the proton's total spin. The remainder arises from gluon spin and from the orbital motion of quarks and gluons inside the proton. For decades, physicists expect the valence quarks to explain nearly everything, but experiments show that the internal accounting is far more distributed. The proton's spin, like its mass, belongs to the whole interacting system. It cannot be understood by looking only at the most obvious components. The proton's stability is equally remarkable. A neutron outside a nucleus decays after a short time because it is slightly heavier than a proton. The proton, by contrast, has no lighter combination of ordinary particles into which it can easily decay while conserving electric charge and other quantum properties. Some theories beyond the established model of particle physics predict that protons eventually decay, but no such event has ever been observed. Experiments watch enormous quantities of matter for extremely long periods, searching for a rare pattern that would signal a proton's disappearance. So far, the proton remains intact. Its endurance allows matter to persist across cosmic history. A universe in which protons vanished quickly could not preserve atoms long enough for stars, planets, or chemistry to develop. The proton is therefore both dynamic within and durable as a whole. That combination is central to the existence of ordinary matter. It changes constantly without becoming something else. Its internal fields surge. Quark pairs arise and vanish. Gluons exchange energy, and momentum shifts among the constituents. Yet the proton remains a proton. Stability in the quantum world is not the absence of change. It is the preservation of certain properties through change. Its identity survives because the underlying interactions constrain the possible outcomes. Durable structures often depend on continuous activity rather than frozen stillness. The proton is one of the earliest and smallest examples of this principle. It becomes the foundation of hydrogen, and hydrogen becomes the main material of stars. Through stellar fusion, protons help create helium and later contribute to the formation of heavier nuclei. Some become part of water molecules, some enter minerals, atmospheres, and living cells. Across all these transformations, the proton's internal complexity remains hidden beneath its simple charge. It behaves as a single positive unit in chemistry, even though its interior is an ocean of quantum motion. This separation between external simplicity and internal complexity makes atoms possible. Chemistry does not need to track every gluon or C-quark. It needs only the proton's stable mass, charge, and nuclear behavior. The deeper turmoil is sealed within a reliable outer identity. The universe builds higher levels of order because each lower level presents stable properties to the next. Quarks and gluons form protons. Protons and neutrons form nuclei. Nuclei and electrons form atoms. Atoms form molecules. Each stage hides much of the complexity below it while preserving the features needed above. The proton therefore stands at a crucial boundary. Beneath it lies the strange confinement of quarks and the self-interacting field of gluons. Above it lies the world of nuclei, elements, and chemistry. Its existence shows that matter is not assembled from tiny inert beads. It is assembled from stable patterns of energy governed by quantum law. The first nuclei can form only because protons and neutrons possess the right masses, charges, and interaction strengths. Their internal complexity does not prevent them from becoming reliable building blocks. Instead, that complexity creates the mass and stability on which the atomic world depends. Once the young universe cools enough, these restless particles begin to join together, opening a brief window in which the first elemental nuclei are forged. The first nuclei emerge during a narrow interval when the young universe is neither too hot nor too cold. Before this window opens, collisions are so violent that any fragile nuclear bond is shattered almost at once. After the window closes, particles move too slowly and spread too far apart for fusion to continue efficiently. Between these limits lies a brief age of construction, lasting only minutes, in which the elemental foundation of the visible universe is established. The ingredients are already present. Protons outnumber neutrons, electrons remain free, and radiation still fills space with enormous energy. What has not yet appeared is a stable nucleus containing more than one particle. The strong nuclear force can bind protons and neutrons, but only across extremely short distances. To feel that force, the particles must approach almost directly, and at first the surrounding heat makes every encounter too destructive. Expansion gradually lowers the temperature, allowing some collisions to end in union rather than separation. The first essential step is the formation of deuterium, a heavy form of hydrogen whose nucleus contains one proton and one neutron. This paired nucleus is called a deuteron. It is simple, but it becomes the gateway to nearly every larger nucleus produced in the early universe. A proton cannot easily build helium by meeting another proton directly. Their positive electric charges repel each other through electromagnetism, creating a barrier that makes close approach difficult. A neutron carries no overall electric charge, so it can enter the range of the strong force more easily. When a proton and neutron combine, the resulting deuteron creates a bridge between the free particles of the plasma and the more tightly bound nuclei that follow. Yet deuterium cannot survive immediately. The early universe contains an immense number of energetic photons for every proton and neutron. Even after the average temperature falls, enough photons remain in the high-energy tail of the radiation distribution to tear deuterons apart. A proton and neutron may bind, release a photon, and become deuterium, only for another photon to strike and reverse the process. This delay is known as the deuterium bottleneck. Nuclear fusion cannot advance until the radiation cools enough for deuterons to survive faster than they are destroyed. The universe therefore holds the necessary particles but waits for the environment to become gentle enough to preserve their first bond. When the bottleneck finally breaks, nuclear reactions accelerate. Deuterons collide with protons and neutrons, producing heavier isotopes of hydrogen and helium. Two deuterons may combine in more than one way, creating helium with 3 nuclear particles or producing tritium, a hydrogen nucleus containing 1 proton and 2 neutrons. These intermediate forms quickly feed further reactions. Helium with 3 particles can capture a neutron. Tritium can capture a proton. Both paths lead toward helium with 2 protons and 2 neutrons, the especially stable nucleus known as helium-4. Its stability is crucial. Once protons and neutrons enter this tightly bound arrangement, they're difficult to remove. Helium-4 therefore becomes the main destination for the neutrons that survive long enough to participate. Each successful fusion step also releases binding energy. The finished nucleus has slightly less mass than the separate particles from which it forms, and the missing mass appears as energy carried away by radiation or motion. This loss of mass is not a defect but a sign of deeper stability. The more tightly bound nucleus sits at a lower energy state, making spontaneous separation less likely. Nuclear construction therefore changes not only arrangement, but the energy balance of matter itself. The abundance of helium is not arbitrary. It follows from the neutron supply available when fusion begins. Free neutrons decay, so their number falls while the universe waits for deuterium to become stable. By the time the bottleneck opens, there is roughly 1 neutron for several protons. Nearly all surviving neutrons are soon locked into helium-4, while the excess protons remain alone. The result is a cosmos containing mostly hydrogen nuclei and a substantial minority of helium nuclei. Measured by mass, roughly 3/4 of ordinary matter emerges as hydrogen, and roughly 1/4 as helium, with only tiny traces of other light nuclei. This simple mixture becomes the raw material for the first stars. The process is called primordial nucleosynthesis because it creates nuclei in the earliest phase of cosmic history. It does not yet create complete atoms. Electrons remain too energetic to bind, and the universe continues as an ionized plasma. What primordial nucleosynthesis establishes is the nuclear inventory that later atoms will inherit. A lone proton will become the nucleus of ordinary hydrogen. A deuteron will become heavy hydrogen. 2 protons and 2 neutrons will become helium. Small quantities of helium-3 and lithium also appear, though far less abundantly. Most heavier nuclei do not form because the reaction network encounters gaps. There is no stable nucleus containing 5 nuclear particles, and no stable nucleus containing 8. These absences create barriers that the rapidly cooling universe cannot easily cross. Helium nuclei may collide, but the short duration and declining density prevent the steady construction of carbon and other heavy elements. The early universe possesses heat, but it lacks the long confinement and pressure later provided by stars. As a result, primordial fusion stops after producing mostly the lightest nuclei. This limitation shapes everything that follows. The first stars are born from hydrogen and helium, not from a rich mixture of elements, carbon, oxygen, silicon, iron, and the many other nuclei needed for rocky planets and complex chemistry must wait. They will be forged much later inside stars, where gravity compresses matter and maintains high temperatures for millions or billions of years. Some elements will form during quiet stellar burning. Others will arise in violent events such as stellar explosions and collisions involving dense stellar remnants. The periodic table is therefore assembled in stages. The early universe provides the light foundation, and generations of stars add heavier layers. Yet the first nuclear era already displays the delicate cooperation among forces that makes atoms possible. The strong force must bind protons and neutrons tightly enough to create stable nuclei. Electromagnetic repulsion must not prevent all positively charged particles from approaching. The weak interaction must regulate the transformations between protons and neutrons. Gravity plays almost no direct role at this scale, but the expansion of the universe determines how quickly temperature and density fall. Nuclear structure and cosmic history meet during these minutes, change the timing, the neutron lifetime, the strength of nuclear binding, or the expansion rate, and the final mixture shifts. Too few neutrons would leave almost pure hydrogen. Too many could lock much more matter into helium. If deuterium were unbound, the path toward helium would fail almost completely. If a stable nucleus with 5 particles existed, heavier elements might form far more easily in the primordial plasma. The universe that actually emerges follows a particular route through these possibilities. Observations preserve evidence of that route. Ancient gas clouds contain hydrogen, helium, and traces of deuterium whose proportions closely match the predictions of primordial nucleosynthesis. These measurements allow cosmologists to test conditions during the first minutes without seeing that era directly. Deuterium is especially valuable because stars tend to destroy it rather than create large amounts of it. Finding deuterium in very old, relatively unprocessed gas provides a record of the early nuclear mixture. Helium offers another clue, though stars can both produce and redistribute it. Together, the light elements act as fossils from a time before stars, galaxies, planets, or atoms in the full sense exist. Their abundances show that the early universe is hot, dense, expanding, and governed by the same nuclear laws measured in laboratories. By the end of primordial nucleosynthesis, the cosmic furnace is already fading. Expansion has lowered the temperature, collisions become less frequent, and the reaction network freezes. The universe is still extraordinarily hot by ordinary standards, but it can no longer push nuclei together efficiently. Hydrogen nuclei remain as solitary protons. Helium nuclei drift through the plasma, a few deuterons, helium-3 nuclei, and lithium nuclei persist among them. Electrons surround this mixture without belonging to any particular nucleus. Light continues to scatter from the free charges, unable to cross great distances. The nuclear skeleton of matter now exists, but the atomic body has not yet formed. The cosmos must continue expanding for hundreds of thousands of years before electrons can settle around these nuclei without being stripped away. Until then, the universe contains the centers of future atoms suspended in a bright and opaque sea. The first elemental pattern is complete, but the first neutral atom still waits. For hundreds of thousands of years, the universe possesses the nuclei of atoms without possessing stable atoms themselves. Protons and helium nuclei drift through a brilliant plasma alongside free electrons, while photons scatter from charged particles so frequently that light cannot travel far in any direction. The cosmos is filled with radiation, yet it remains opaque. Every region glows, but no distant region can be seen through another. The ingredients of transparency are present, though they have not yet settled into the arrangement that will allow space to clear. Expansion continues steadily, stretching wavelengths, lowering temperatures, and reducing the energy of collisions. At a certain point, electrons can remain attached to nuclei for longer than the surrounding radiation can tear them away. The universe then crosses from a plasma of separated charges into a gas dominated by neutral atoms. This transition is called recombination, although the name is historically misleading because electrons and nuclei are combining for the first time rather than reuniting after an earlier atomic age. It creates the first long-lived atoms and releases the oldest light that can still be observed. The process begins mainly with hydrogen, because hydrogen nuclei are simply protons and are far more abundant than all other nuclei. A proton carries positive electric charge, while an electron carries an equal negative charge. Electromagnetism draws them together, but in the hot plasma attraction alone is not enough. When an electron approaches a proton, it must lose energy to become bound. It can do this by emitting a photon and dropping into an allowed atomic state. Yet the surrounding radiation contains many photons energetic enough to reverse the event. A newly formed hydrogen atom can absorb one of them and become ionized again, releasing its electron back into the plasma for a long time. Creation and destruction remain almost balanced, with destruction winning often enough to prevent neutral atoms from becoming common. Cooling gradually changes those odds. The average photon loses energy as space expands, and fewer photons remain capable of breaking hydrogen apart. Once the radiation becomes gentle enough, bound atoms begin to accumulate. The temperature is still several thousand degrees, far hotter than the surface of many ordinary stars. But temperature alone does not determine the outcome. The crucial factor is the relationship between the photon population, the matter density, and the binding energy of hydrogen. There are enormously more photons than atomic nuclei, so recombination begins at a temperature much lower than a simple comparison with hydrogen's binding energy might suggest. Even when most photons are too weak to ionize hydrogen, a small high-energy fraction remains dangerous because photons are so abundant. Only after expansion suppresses that energetic tail can neutral atoms survive in large numbers. The path is also slowed by the internal structure of hydrogen. An electron captured directly into the lowest energy state may emit a photon energetic enough to ionize another nearby atom, undoing part of the progress. More effective routes involve capture into higher atomic states followed by a sequence of transitions. In one important pathway, the electron passes through a long-lived excited state, and releases two lower energy photons instead of one highly energetic photon. These photons are less able to ionize other atoms, allowing neutral hydrogen to accumulate. Another pathway involves the escape of particular photons from resonance with surrounding atoms as expansion stretches their wavelengths. Recombination is therefore not a single universal instant. It is an extended quantum process shaped by atomic transitions, photon transport, and cosmic expansion. Different atoms settle at slightly different times, and the fraction of free electrons declines over a broad interval. Helium follows its own sequence. A helium nucleus contains 2 protons and usually 2 neutrons, giving it twice the positive electric charge of hydrogen. It must capture 2 electrons to become neutral. Because its binding energies differ from those of hydrogen, helium passes through stages, first becoming singly ionized and later neutral. Much of this occurs before hydrogen recombination is complete. Even so, hydrogen dominates the overall change because it is so abundant. As free electrons disappear into atoms, the plasma loses the charged particles that have been scattering light. The average distance a photon can travel increases rapidly. The opaque cosmic fog begins to thin. Matter changes its electrical organization. A neutral atom can still interact with light, but it does not scatter the surrounding radiation as efficiently as a free electron does under these conditions. Positive and negative charge now sit together in compact structures, and vast regions become transparent. The change resembles no ordinary clearing of smoke, because nothing is blown away and no external wind passes through. Photons that have spent hundreds of thousands of years repeatedly scattering suddenly begin to move freely across expanding space. The moment of their final scattering forms a kind of luminous boundary around every observer in the later universe. It is called the surface of last scattering, though it is not solid. It is the distant shell from which ancient photons last interact strongly with matter before travelling almost undisturbed. Those photons now arrive as the cosmic microwave background. At the time of release, the radiation is hot enough to glow mainly in visible and infrared wavelengths, giving the young universe a warm brilliance. As space expands over billions of years, the wavelengths stretch into the microwave range and the radiation cools to only a few degrees above absolute zero. The light becomes invisible to human eyes, but sensitive instruments can map it across the entire sky. Its existence confirms that the early universe passes through a hot, dense, ionized state before atoms form. Its tiny variations preserve a record of density differences present when recombination occurs. Some regions are slightly hotter or denser than others. These variations are minute, but gravity will amplify them across immense spans of time. The denser regions attract more matter, eventually contributing to the formation of galaxies, clusters, stars, and planets. Recombination, therefore, does more than create neutral atoms. It reveals the pattern from which later cosmic structure grows. The universe becomes transparent at almost the same stage that it leaves behind its earliest visible portrait. Yet the formation of atoms does not mean that every electron finds a nucleus immediately. A small fraction remains free, and later processes alter the balance again. When the first stars ignite, their ultraviolet radiation begins to ionize surrounding hydrogen. Galaxies and energetic objects gradually reionize much of intergalactic space, stripping electrons from atoms once more. Even today, much ordinary matter between galaxies exists as ionized plasma rather than neutral gas. Atoms can be created, broken apart, and recreated many times. Their importance lies not in being permanent under all conditions, but in being stable whenever the environment becomes cool and calm enough. They are favoured states of matter across a wide range of temperatures and densities, Once electrons settle into allowed quantum states, atoms can endure without continuously radiating away their energy. The lowest energy configuration provides stability, while higher states allow atoms to absorb and emit light in precise patterns. These spectral lines later become one of astronomy's most powerful tools. Each element interacts with light at characteristic wavelengths determined by its electron structure. Long after recombination, those patterns reveal the composition, temperature, and motion of distant stars and gases. The same quantum rules that allow the first atoms to survive also allow matter to announce its identity across space. Recombination is therefore both an ending and a beginning. It ends the long era in which radiation and matter are tightly coupled in an opaque plasma. It begins the transparent universe, where light can cross enormous distances and matter can gather under gravity with less resistance from radiation. It creates neutral hydrogen and helium, the quiet gas from which the first stars will form. It releases a fossil glow that still surrounds the cosmos. Most importantly, it completes the first atom. The proton has existed for hundreds of thousands of years. The electron has existed even longer. Only now do they become a lasting whole. Their union is not a collision that produces a tiny solid object, but the establishment of a stable quantum relationship. The electron spreads into an allowed state around the nucleus, giving the atom size, neutrality, and the capacity for chemistry. From this point onward, the universe contains matter that can bond, cool, collect, and diversify. The era of separated ingredients gives way to the era of atomic structure, and the ancient light escaping at that transition begins a journey that will continue until it enters the instruments of a much later cosmos. When the first neutral atoms form, light finally gains a path through the universe. For hundreds of thousands of years, photons have been trapped in an opaque plasma, scattered again and again by free electrons. Their movement is not stopped, but it is endlessly redirected, like a message passed through a crowd so dense that no straight route remains. Recombination changes that condition. Electrons settle into bound states around nuclei. The number of free charges falls sharply, and the average distance a photon can travel expands from a tiny interval to an almost cosmic span. Radiation that has been imprisoned since the early universe now begins to move freely. The escape is not a sudden flash from a single location. It happens everywhere, across all space. As matter becomes transparent, every region releases light, and that light begins crossing an expanding universe whose future galaxies, stars, and planets have not yet formed. The photons carry with them a record of the conditions at their last interaction with matter. They preserve temperature, density, motion, and the imprint of sound waves passing through the ancient plasma. This radiation is the cosmic microwave background, the oldest light that can still be observed. It is not light from the first stars, because stars do not yet exist. It is older, released when the universe is only a small fraction of its current age. At the moment of departure, the radiation has a warm glow, concentrated near visible and infrared wavelengths. Over billions of years, cosmic expansion stretches those wavelengths. Each crest of the electromagnetic wave is carried farther from the next as space grows. The light loses energy and shifts through the infrared into the microwave region. Today it fills the sky with a temperature only a few degrees above absolute zero. It arrives from every direction because every observer is surrounded by distant regions where the early plasma becomes transparent. The result is not a picture of one remote object, but a view of an ancient surface enclosing the observable universe. Looking farther into space also means looking farther into the past, and the microwave background marks the limit beyond which ordinary light cannot reveal earlier times. Before recombination, photons scatter too often to preserve a clear image. The universe beyond that luminous boundary is hidden behind its own opacity. The cosmic microwave background is therefore both a beginning and a veil. It is the first freely travelling light and the last light from the era before atoms dominate matter. Its near uniformity is one of its most striking features. The temperature is almost the same in every direction, suggesting that the young universe is remarkably smooth. Yet the smoothness is not perfect. Tiny differences appear across the sky. Variations far smaller than ordinary temperature changes. These faint irregularities are essential. They mark regions that contain slightly more or slightly less matter and radiation than average. In the denser regions, gravity has a marginally stronger pull. Over immense spans of time, this advantage grows. Matter falls toward matter, concentrations deepen, and the first simple variations become the seeds of galaxies and galaxy clusters. Every large structure in the modern cosmos can trace part of its history to these slight imbalances preserved in the ancient light. The microwave sky is therefore not a blank glow. It is a map of possibility before the visible universe takes shape. The patterns also record pressure waves that move through the early plasma. Gravity tries to compress denser regions, while radiation pressure pushes them outward. The competition produces oscillations, vast sound waves travelling through the hot mixture of particles and light. These are not sounds that move through air, but pressure changes in the cosmic plasma. Their scales are enormous, and their frequencies are far below anything associated with ordinary hearing. When recombination occurs, the plasma loses the free electrons that keep radiation tightly coupled to matter. The waves can no longer continue in the same form, and their pattern becomes frozen into the distribution of matter and the temperature of the released light. The traces are known as baryon acoustic oscillations. They remain visible in two different records: the small variations of the microwave background and the later spacing of galaxies across the universe. A pressure wave from the age before atoms leaves a measurable preference in the architecture of galaxy clusters billions of years later. This continuity links the smallest early fluctuations with the largest later structures. The atoms that free light also preserve the last motion of the plasma from which those atoms emerge. For much of human history, this radiation is unknown. The night sky appears dark between the stars, and nothing suggests that space is filled with ancient microwave light. Its discovery depends on both theoretical prediction and accidental detection. Physicists studying a hot expanding universe realize that radiation from the early plasma should still exist, cooled by expansion but not destroyed. The prediction receives little attention at first. Years later, radio astronomers working with a sensitive antenna encounter a persistent background hiss that seems to come from every direction. They remove possible sources of interference, equipment is checked, local signals are considered, and even material left by birds inside the antenna is cleaned away. The noise remains. Its uniformity and wavelength match the expected remnant of the hot early universe. What appears as unwanted interference becomes one of the clearest pieces of evidence for cosmic history. The signal confirms that the universe once passes through a hot, dense state, and later cools enough for atoms to form. It also allows that ancient transition to be studied in extraordinary detail. Later instruments rise above much of Earth's atmosphere and map the microwave background across the whole sky. Each generation measures the temperature variations with greater precision. The broad glow becomes a finely textured field of warmer and cooler patches. From their size and distribution, cosmologists infer the geometry, composition, and expansion history of the universe. The data reveal how much ordinary matter exists, how much unseen matter influences gravity, and how the early fluctuations are arranged. These conclusions do not come from seeing atoms directly at recombination. They come from reading the light released when those atoms form. The radiation acts as a messenger whose journey lasts almost the entire age of the cosmos. It crosses regions that later become galaxies, passes through changing gravitational fields, and continues to cool as space expands. Along the way, subtle effects alter parts of the signal. Hot gas in galaxy clusters can shift the energy of some photons. Large concentrations of matter bend their paths through gravitational lensing. The growth of cosmic structure leaves additional traces. Yet beneath these later modifications, the original pattern remains. The microwave background is ancient without being untouched. It carries both the conditions of its birth and the history of the universe through which it travels. Its existence gives atoms a role far beyond chemistry. The first stable atoms do not merely allow matter to become neutral. They change the visibility of the cosmos. Before them, light and matter behave as one tightly coupled medium. After them, radiation can move independently while matter begins gathering more freely under gravity. The universe separates into a transparent background of travelling photons and a darkening network of gas that will eventually collapse into stars. The release of light marks the beginning of the cosmic dark ages, a period when the microwave glow fades into wavelengths no eye can see, and no new stars yet shine. Neutral hydrogen fills space, transparent to much of the relic radiation but capable of absorbing particular wavelengths. Gravity slowly deepens the early density variations. The first luminous objects remain in the future. For a time, the cosmos contains atoms, darkness, and the fading echo of its own formation. That echo never disappears. It grows colder and weaker, but it continues to fill space. Every location is immersed in it. The ancient photons pass through planets, bodies, instruments, and empty interstellar regions, usually without interaction. They are reminders that the atomic world has a beginning, and that the moment of its arrival leaves a physical trace. The first atoms are not witnessed by later observers directly, yet their formation is written across the sky. The evidence arrives as a quiet microwave glow, nearly uniform, delicately patterned, and older than every star. In that light, the universe preserves the instant when opacity gives way to transparency, and scattered particles become stable structures. The first atoms leave an echo because their birth changes what light is allowed to do. Their existence opens the universe, and the radiation released through that opening continues its journey through cosmic time. An atom is held together by attraction, yet attraction alone seems to predict its destruction. The positively charged nucleus pulls on the negatively charged electron, and in the language of ordinary motion the electron should lose energy, spiral inward, and eventually fall into the nucleus. Classical physics once led directly to this conclusion. A charged particle moving in a curved path should radiate energy. If the electron were a tiny planet circling the nucleus, it would continuously emit light, slow down, and collapse. Every atom would be unstable. Matter could not preserve its shape. Chemistry would not have time to exist. Yet atoms endure for immense spans, and electrons do not steadily crash inward. The reason is not that the attraction is weak. Electromagnetism binds the atom strongly enough to create lasting structure. The reason is that the electron does not behave like a miniature object following a definite track. Its motion belongs to the quantum world, where position, momentum, energy, and probability are connected by rules with no exact equivalent in ordinary experience. Atomic stability begins when the familiar picture of an orbit gives way to the less intuitive idea of a quantum state. A quantum state describes the possible outcomes for an electron and the probabilities associated with them. It does not assign the electron a hidden path that remains unknown only because instruments are imperfect. Instead, the spread of possible positions is part of the electron's physical condition. Around a hydrogen nucleus, The lowest energy state forms a smooth probability cloud centered on the proton. The cloud does not show a substance smeared through space in the ordinary sense. It represents where a measurement is likely to find the electron. Before such a measurement, the electron is not simply waiting at one concealed point. Its state extends across the region allowed by the atomic structure. This spread gives the atom most of its size. The nucleus is tiny and contains nearly all the mass, while the electron's quantum state reaches far beyond it. Matter occupies space because electrons cannot be confined without consequence. The key principle is uncertainty. The more tightly an electron is confined to a small region, the less precisely its momentum can be defined. A narrow position requires a wide range of possible momenta, and that range corresponds to greater kinetic energy. If the nucleus pulls the electron inward, the electric potential energy decreases, favouring a smaller atom. But squeezing the electron into an ever smaller region raises its kinetic energy. These tendencies oppose each other. The atom settles into a lowest energy state where the attraction to the nucleus and the quantum cost of confinement reach a balance. The electron does not avoid the nucleus because a solid barrier blocks the way. It remains spread out because complete localization would demand enormous momentum, uncertainty, and therefore enormous energy. Stability emerges from quantum mechanics itself. This lowest state is called the ground state. It is not a tiny orbit with the electron moving along a ring. It is the minimum energy pattern available to the entire electron nucleus system. Once the electron occupies it, there is no lower atomic state into which it can fall while preserving the same structure. The electron may emit energy when dropping from an excited state to the ground state, but after reaching the minimum it cannot continue radiating in the classical manner. The atom stops losing energy because quantum energy comes in allowed levels rather than a continuous range. This quantization follows from the wave nature of matter. Only certain standing wave patterns fit around a nucleus in a self-consistent way. Other patterns interfere with themselves and do not form stable states. The allowed states become the orbitals of the atom. An orbital is a quantum pattern defined by energy and spatial probability. Some are roughly spherical. Others form lobes or more complicated shapes. These forms determine how atoms bond and therefore how chemistry unfolds. The stability of a stone, a molecule of water, or a strand of genetic material ultimately depends on these permitted electron patterns. Each electron also carries an intrinsic property called spin. Spin behaves mathematically like angular momentum, though the electron is not a tiny sphere rotating in space. It is a fundamental quantum characteristic. Spin helps govern how electrons can share atomic states. Another rule, the exclusion principle, says that no two identical electrons in the same atom can occupy exactly the same complete quantum state. Because electrons resist being placed into identical states, they fill orbitals in an ordered sequence. The lower states fill first, then higher ones. This layered arrangement produces electron shells and gives each element its characteristic chemical behavior. Hydrogen has one electron. Helium fills the lowest orbital with 2 electrons of opposite spin. Larger nuclei hold more electrons, which occupy increasingly complex arrangements. The periodic table arises from the repeated filling of these quantum states. Atomic stability therefore does more than prevent collapse. It organizes matter into distinct chemical identities. Electromagnetism provides the attraction, but quantum mechanics determines the architecture. The electric force draws electrons toward the nucleus, while electron wave behavior, uncertainty, and exclusion prevent them from collecting in the same small region. Inner electrons remain close to the nucleus and are held tightly. Outer electrons extend farther and interact more readily with neighbouring atoms. These outer electrons form chemical bonds, transfer between atoms, or become shared across molecules and solids, because electron energies are quantized. Atoms absorb and emit light only at particular frequencies. A photon can raise an electron to a higher state only if it carries the required energy. When the electron returns to a lower state, a photon of corresponding energy is released. Each element therefore produces a distinctive pattern of spectral lines. Those patterns allow atoms to be identified in distant stars and planetary atmospheres. The same quantum structure that keeps matter stable also gives it a recognizable signature in light. When two atoms approach, their electron clouds respond to one another. Attraction can create a bond, while exclusion and electric repulsion resist excessive overlap. This is why atoms can connect without collapsing into a single dense point. Molecules preserve separations set by balances among attraction, repulsion, and quantum structure. Solids resist compression because forcing atoms closer drives electrons into higher energy arrangements and strengthens repulsive interactions. The firmness of ordinary matter is therefore another expression of quantum stability. A table supports weight because its electrons cannot all be rearranged into smaller and smaller volumes without an energetic cost. The atom is stable, but it is not unchangeable. Enough energy can remove an electron, producing an ion. A photon can excite an electron to a higher state. Collisions can distort electron clouds, break chemical bonds, or strip atoms apart completely. In stars and hot plasmas, atoms may remain ionized for long periods. Under extreme pressure, ordinary atomic structure can disappear. Stability always belongs to a range of conditions. Atoms endure across much of the cool universe because the surrounding energy is usually too low to overcome their binding, not because they are indestructible in every environment. Their success comes from being stable enough for complexity while remaining flexible enough for change. A perfectly rigid form of matter could not support chemistry. A form that broke apart too easily could not preserve information. Atoms occupy the middle ground. Their nuclei endure, their electrons rearrange, and their outer structures respond to the environment. They can form bonds and later release them. They can absorb light, store energy, and emit it again. They can join crystals, gases, liquids, and living molecules without losing the identities that make those structures meaningful. The remarkable feature is that this balance rests on uncertainty rather than certainty. The electron does not survive because its exact path is protected. It survives because no exact path exists. Its spread of possibilities prevents unlimited collapse. The atom is orderly because its components are described by probability. At the foundation of solid matter lies not a clockwork mechanism of tiny bodies, but a stable quantum pattern whose outcomes can be predicted only statistically. This does not make the atom vague or unreliable. Quantum theory predicts its energies, spectra, and behavior with extraordinary precision. The uncertainty belongs to individual outcomes, while the structure of probabilities remains exact. From that strange combination, the dependable world emerges. Atomic stability is not a compromise hiding a defect in knowledge. It is one of nature's central organizing principles. Electromagnetic attraction gathers particles into bound systems. Quantum mechanics sets the allowed forms. Uncertainty resists confinement. Exclusion builds shells. Quantized energy prevents endless collapse. Together, these rules create atoms that can persist across billions of years and still react in fractions of a second. Once stable atoms exist, the universe gains a library of distinct elements and a way to combine them. The next mystery is how these separate quantum structures begin to share electrons, form bonds, and build the vast chemical complexity of planets and life. Once atoms become stable, the universe gains more than durable pieces of matter. It gains a way for those pieces to recognize, attract, repel, exchange, and combine with one another. The nucleus determines which element an atom is, but the electrons determine how that element behaves. They shape the atom's outer boundary, set the energies available for interaction, and decide whether neighbouring atoms remain separate or become part of a larger structure. Chemistry begins in these electron arrangements. It is not a new force added to nature, but the large-scale expression of electromagnetism and quantum mechanics acting together. The same principles that keep an electron from collapsing into a nucleus also guide electrons as atoms approach. Their probability clouds overlap, their allowed states shift, and new patterns become possible across more than one nucleus. A molecule forms when the combined arrangement has lower energy than the separated atoms. Matter begins to build not by stacking rigid spheres, but by reorganizing quantum states. Hydrogen provides the simplest example. Each hydrogen atom contains one proton and one electron. When two hydrogen atoms approach, their electrons can occupy a shared state extending around both nuclei. The positive nuclei repel one another, and the electrons repel one another, yet each electron is attracted to both protons. At the right separation, these forces balance in a way that lowers the total energy. The result is a hydrogen molecule, two nuclei held together by a shared electron structure. The bond is not a physical rod placed between the atoms. It is a stable distribution of probability and charge. If the nuclei move too close, repulsion rises sharply. If they move too far apart, the shared state can no longer hold them together. The molecule settles around a characteristic distance, vibrating and rotating while preserving its identity. This first bond introduces a principle that will repeat through almost every material world. Stability often comes from sharing. Other atoms form bonds in different ways. Some transfer electrons almost completely, creating positively and negatively charged ions that attract each other. This ionic bonding builds crystals such as salts, where enormous repeating lattices replace isolated molecules. Some atoms share pairs of electrons in covalent bonds, producing structures ranging from simple gases to long biological chains. Metals organize their outer electrons into states spread across many nuclei, creating a mobile electron population that carries electric current and heat. Weak attractions also arise from temporary shifts in electron clouds, allowing neutral molecules to cling together. Hydrogen bonds, weaker than ordinary covalent bonds but powerful in large numbers, help shape water, proteins, and genetic molecules. Chemistry becomes diverse because electrons can be held tightly, shared, transferred, or spread across a solid. The possibilities are governed by the architecture of electron shells. Atoms with nearly complete outer shells tend to resist reaction. Atoms with one or two loosely bound outer electrons often release them. Others seek additional electrons or share them to complete stable arrangements. These repeating patterns create the structure of the periodic table. Elements in the same column often behave similarly because their outer electrons follow related patterns. Atomic number increases one proton at a time. Yet chemical properties recur in cycles because electron states fill in ordered layers. The universe therefore turns a simple sequence of nuclear charge into a repeating landscape of behavior. A small collection of quantum rules produces metals, gases, salts, minerals, acids, pigments, and countless molecular forms. Carbon becomes especially important because it can form several strong covalent bonds at once. Its electrons allow it to connect with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and other carbon atoms in many geometries. It builds chains, rings, branches, sheets, and three-dimensional frameworks. Carbon does not contain a special force for life. Its importance comes from versatility. It forms bonds stable enough to preserve complex structures but responsive enough to be rearranged by chemical reactions. From carbon chemistry emerge sugars, fats, proteins, and the molecular systems that store genetic information. Yet none of these possibilities matter until stars expand the elemental inventory. The first atoms are mostly hydrogen and helium, with only faint traces of a few other light elements. Gravity gathers this gas into dense regions. As the first stars form, their cores become hot enough for nuclear fusion. Hydrogen nuclei combine into helium, and later stellar stages produce carbon, oxygen, neon, silicon, and other elements. Massive stars build nuclei in successive layers until fusion reaches iron, beyond which ordinary fusion no longer releases energy efficiently. Explosions, stellar winds, and collisions involving compact remnants scatter newly forged elements into space. The atoms required for rocks, oceans, atmospheres, and bodies are therefore products of stellar history. Chemistry on a planet begins with nuclei assembled in stars and electron structures established by quantum law. Enriched clouds of gas and dust later collapse around new stars. Tiny solid grains collide and stick. Minerals condense according to temperature, pressure, and elemental abundance. Carbon compounds freeze onto cold particles. Silicates form rocky dust. Metals collect in dense fragments. Over time, gravity draws these materials into larger bodies. The chemistry of atoms becomes the geology of planets. Bond strengths determine which minerals survive heat, which substances evaporate, and which compounds dissolve in liquid. Atomic size influences crystal structure. Electric charge guides how ions fit into mineral lattices. The shape of continents, the flow of magma, and the strength of stone all descend from electron behavior at scales too small to see. Water reveals this ascent from quantum structure to planetary consequence with unusual clarity. A water molecule contains one oxygen atom bonded to two hydrogen atoms. Its shape is bent rather than straight because the electron pairs around oxygen arrange themselves according to quantum and electrical constraints. Oxygen pulls shared electrons more strongly than hydrogen, giving the molecule an uneven distribution of charge. One side becomes slightly negative and the hydrogen side slightly positive. This polarity allows water molecules to attract one another through hydrogen bonds. Those weak bonds give water properties essential to planetary environments. Water remains liquid across a broad range of temperatures, absorbs large amounts of heat, dissolves many ionic and polar substances, and expands when it freezes because its molecules settle into an open crystal structure. Ice therefore floats, insulating the liquid beneath it. Oceans store heat and move it around planets. Water carries dissolved minerals, supports chemical reactions, and shapes landscapes. These features grow from the geometry and charge distribution of a molecule built from three atoms. Complexity continues when molecules begin forming networks of reactions. Some reactions release energy, others store it in new bonds. Catalysts lower the barriers that slow rearrangement, allowing transformations to occur under gentler conditions. In living systems, proteins act as selective catalysts because their folded shapes guide particular molecules into precise positions. Their shapes come from sequences of amino acids held together by covalent bonds, hydrogen bonds, ionic attractions, and the behavior of water. Genetic molecules preserve information in an ordered chain of chemical units. Cell membranes form because certain molecules contain one region attracted to water and another that avoids it. Placed in water, they spontaneously assemble into boundaries. Life uses chemistry, but chemistry does not aim toward life. Most molecular reactions in the universe remain non-living. The important point is that atoms make persistent complexity possible. They allow structures to hold information, respond to energy, and undergo controlled change. An atom can remain itself while joining a molecule. A molecule can remain recognizable while becoming part of a cell. Stable lower levels support flexible higher ones. The universe does not need to rebuild matter from quarks for every new arrangement. It can work with atoms as reliable units, rearranging their electrons while leaving most nuclei intact. This separation of scales makes complexity efficient. Nuclear reactions require extreme conditions. But chemical reactions unfold in cold clouds, warm oceans, rocky crusts, atmospheres, and living tissue. Vast diversity becomes possible without altering the elemental cause. The same carbon atom can pass through a star, a gas cloud, a mineral, an ocean, and a cell while retaining its nucleus. Its bonds change, its partners change, and its role changes, but its atomic identity persists. Everything familiar is made of atoms because atoms occupy a rare middle ground between the fundamental and the complex. They are small enough to combine in immense numbers, stable enough to endure, and flexible enough to rearrange. Their electron structures translate quantum law into chemistry, and chemistry translates atomic possibility into worlds. Once the first atoms appear, the universe is no longer limited to plasma and radiation. It gains molecules, dust, crystals, oceans, atmospheres, and eventually systems capable of preserving and copying information. Yet this richness depends on balances that are easy to disturb. The same forces that make bonding possible must have the right strengths, and the particles inside atoms must possess the right masses and charges. Chemistry is abundant in this universe, but its foundation may be far more delicate than its familiarity suggests. A universe filled with atoms can appear secure, as though stable matter follows naturally from the existence of particles and forces. Yet the deeper the atomic structure is examined, the more conditional it becomes. The atom survives only because several properties of nature fall within ranges that allow nuclei to form, electrons to remain bound, and chemistry to unfold without immediate collapse. This does not mean that every constant is adjusted with perfect precision, or that physics already knows how wide every possible range may be. It means that the ordinary matter of the cosmos depends on relationships that could, in principle, have been different. Change the strengths of forces, the masses of particles, or the balance between them, and the universe may still exist while atoms do not. The familiar world rests on a delicate network of compatibility. At the center of this network is the competition between electromagnetism and the strong nuclear force. Electromagnetism attracts electrons to nuclei and allows atoms to bond, but it also pushes positively charged protons apart. The strong force overcomes that repulsion at very short distances and binds protons and neutrons into nuclei. If the strong force were much weaker, many nuclei would fall apart. Deuterium, the simple union of one proton and one neutron, might fail to remain bound. Without stable deuterium, the early universe would struggle to build helium, and stars would lose one of the key pathways by which hydrogen fusion proceeds. The periodic table would be sharply reduced, perhaps leaving a cosmos dominated by isolated hydrogen. Such a universe could contain atoms, but chemistry would be far poorer, and the heavier elements required for rocky planets and living systems might never appear. If the strong force was stronger, a different problem could arise. Two protons might bind directly into a stable diproton in the actual universe. No stable diproton exists under ordinary conditions. The inability of two protons to remain bound slows hydrogen fusion inside stars. This delay is essential. Stars release energy gradually because proton fusion begins through weak interaction processes that occur only rarely. If diprotons formed easily, stellar fusion could proceed far more rapidly. Hydrogen might be consumed much sooner, altering the lifetimes and structures of stars. The universe could become bright and violent for a shorter era, with less time for stable planetary environments to develop. A modest change in nuclear binding could therefore reshape cosmic history from the first minutes onward. The neutron and proton masses introduce another balance. A neutron is slightly heavier than a proton. That difference allows a free neutron to decay while leaving the proton stable. It also permits neutrons to remain bound inside many nuclei. If the neutron were lighter than the proton by enough, protons could transform into neutrons under ordinary conditions. Hydrogen nuclei might disappear, and the simplest atom would no longer survive in its familiar form. If the neutron were much heavier, too few neutrons might remain available for building complex nuclei. The mass difference is connected partly to the unequal masses of up and down quarks, and partly to electromagnetic effects inside the particles. Several contributions nearly cancel, leaving the small difference observed. Atomic matter depends on the result. The electron mass matters as well. Electrons must be light enough to form large atomic structures around tiny nuclei. Their small mass gives atoms a scale far greater than the nuclei at their centres. If electrons were much heavier, their quantum states would contract closer to the nucleus, reducing atomic size and changing bond energies. Chemistry would become more tightly bound and could behave very differently. If electrons were too light, atoms would become larger and more fragile, with outer electrons more easily removed. The exact consequences would depend on other constants. But the central point remains: the character of matter is set by ratios, not isolated numbers. A particle mass becomes meaningful through its relationship to the masses and forces around it. Electromagnetism must also occupy a suitable range, strengthen it, and electrons bind more tightly while proton repulsion inside nuclei grows. Weaken it, and electrons become easier to remove. Bonds become less secure, and atoms swell. The same force must support both atomic stability and chemical flexibility. It must be strong enough for electrons to remain attached under ordinary conditions, but not so overwhelming that matter becomes locked into rigid, inaccessible states. Chemistry requires a middle ground in which bonds can form, persist, and break. Living systems depend especially on this balance, because metabolism and replication require structures that are stable over useful times yet responsive to modest flows of energy. Too much stability would prevent rearrangement. Too little would erase structure before information could be preserved. Even the dimensional structure of space plays a role. In 3 spatial dimensions, electric attraction weakens with the square of distance, and quantum mechanics allows stable orbital states around nuclei. In spaces with different numbers of large dimensions, the mathematical behavior of forces and orbits changes. Some such worlds might not support stable atoms or planetary systems in recognizable forms. The architecture of matter is therefore connected not only to particle properties, but also to the geometry through which forces act. Atoms are possible because fields spread through space in a particular way. The universe does not merely contain matter. It provides a stage whose structure helps determine whether matter can organize. None of these observations alone proves that the laws are adjusted for atoms. Physics does not yet know whether the constants could truly vary independently. A deeper theory may eventually show that many apparent choices are fixed by a single underlying structure. What now looks like a collection of adjustable settings could turn out to be the only self-consistent outcome of more fundamental laws. In that case, atoms may be less accidental than they appear. The apparent delicacy could reflect limited knowledge rather than genuine freedom. Yet no accepted theory currently derives every relevant particle mass and force strength from necessity. Many values are measured experimentally and inserted into existing equations. Their deeper origin remains unknown. This gap creates the fine-tuning question. Fine-tuning does not necessarily mean that the universe was tuned by an agent. In physics, the phrase can describe sensitivity. Small changes in assumptions or parameters produce large changes in outcomes. It identifies a puzzle before it identifies an explanation. Atomic existence appears sensitive to several balances, but the degree of sensitivity depends on how changes are defined and whether multiple constants vary together. A stronger force might be offset by a different particle mass. A universe unlike this one could still produce structures that are not immediately obvious from changing one value at a time. Caution is therefore necessary. The absence of familiar atoms does not always imply the absence of all complexity. Unknown forms of stable matter may be possible under different laws. Still, the atoms known in this universe occupy a constrained region of physical possibility. Their nuclei must hold together. Their electrons must remain in bound states. Stars must live long enough to forge and distribute heavier elements. Chemistry must operate across useful temperatures. Expansion must permit matter to cool and gather. The requirements span scales from quarks to galaxies. A change at the smallest level can echo outward through cosmic history, alter nuclear binding, and primordial element abundances shift. Alter stellar fusion, and star lifetimes change. Alter electron structure, and molecules behave differently. Alter molecular behavior, and planets develop along unfamiliar paths. The universe is layered, so sensitivity at one layer becomes consequence at the next. The abundance of atoms can therefore conceal their fragility. They are everywhere in ordinary experience, but their universality follows from a specific physical framework. Once the framework permits stable atoms, atoms naturally become common because they are durable and because cosmic cooling favors them across large regions. Their success does not erase the question of why the framework permits them, it sharpens it. The same laws that make atoms ordinary also reveal how easily other possibilities can be imagined in which atomic matter never forms, never lasts, or never becomes chemically rich. The world of stone, water, air, and life stands not on a single coincidence, but on a chain of compatible conditions. Whether that chain is necessary, accidental, selected, or part of something larger remains unresolved. The atom endures, while the reason its foundations fit together so well opens into a deeper mystery about the universe itself. Why this universe contains atoms is a question that reaches beyond atomic physics. The structure of the atom can be described with extraordinary precision. Quantum mechanics predicts its energy levels. Electromagnetism explains the attraction between nuclei and electrons. Nuclear physics explains why some nuclei remain stable while others decay. Cosmology explains how expansion cools the early universe enough for atoms to form. Together, these theories show how atoms exist and how they behave. They do not yet reveal why the laws and constants take the particular forms that make atoms possible. At that boundary, explanation begins to divide into several paths. One possibility is necessity, perhaps a deeper theory, still undiscovered, allows no real freedom in the values of particle masses or force strengths. What appear to be separate settings may emerge from one underlying mathematical structure: the electron mass, the quark masses, the strength of electromagnetism. And the behavior of the strong force might be linked by principles not yet visible in current theories. If so, atoms may not result from a fortunate arrangement among many possible arrangements. They may follow inevitably from the only internally consistent form that physical law can take. This possibility has a certain elegance. Science often advances by showing that apparently independent facts share a common cause. The motions of falling stones and orbiting moons become expressions of gravity. Electricity and magnetism become aspects of one electromagnetic field. Space and time become parts of a single geometry. it is reasonable to wonder whether the properties that permit atoms may eventually be united in the same way. Yet necessity remains a hope rather than an established answer. Existing theories still contain values that must be measured. The Standard Model of particle physics describes known particles and interactions with great success, but it does not explain why every mass and coupling has the value observed. A deeper framework may remove this freedom, reduce it, or merely move the unexplained choices to another level. Even a final theory could possess several possible solutions, each describing a universe with different low-energy laws. Necessity cannot be assumed simply because it would be satisfying. A second possibility is chance. The constants may have no deeper reason for their values. They may simply be facts about this universe, fixed without purpose or further explanation. In that case, atoms exist because the physical conditions happen to permit them. Chance can feel incomplete, but it is not logically impossible. Every specific outcome must be one outcome rather than another, and not every fact must have an accessible cause. A shuffled deck settles into one exact order, however unlikely that order appears when considered in advance. The improbability of a particular arrangement does not by itself prove design or deeper necessity. Yet the comparison becomes difficult when only one universe is available for observation, and the range of possible values remains unknown. Probability requires a way to define alternatives and assign weights to them, without a tested theory describing how constants vary. Numerical claims about the odds of atoms can become speculative. It is possible to show that certain changes would disrupt familiar matter. It is much harder to calculate how likely those changes are within a real space of possible universes. Chance therefore remains possible, but its meaning is unclear until physics knows what is being randomly selected and by what process. A third path begins with selection. Any observer able to ask why atoms exist must already inhabit a universe where complex structure is possible. This simple fact creates an observational filter, a universe without stable matter, long-lived stars. Or chemistry would contain no beings capable of noticing its absence. Observations are therefore not drawn from all imaginable universes without bias. They come only from regions compatible with observers. This reasoning is known as the anthropic principle, though the name can sound more human-centered than the idea truly is. The principle does not claim that the universe is designed for humanity, or that human life occupies a preferred cosmic position. It says only that observation requires conditions that allow observers to arise. If many environments exist with different physical properties, the observed environment will necessarily belong to the subset where observation is possible. Selection effects are familiar in other sciences. Fish caught by a net reflect the size of the net's openings. Stars detected by a telescope reflect the sensitivity of the instrument. A sample can appear unusual because the method of observation excludes everything else. Applied to cosmology, the observer becomes part of the selection process. Stable atoms may look surprising across a broad range of theoretical possibilities, but any atomic observer must find stable atoms nearby. This reasoning can clarify why observation alone cannot distinguish luck from necessity. It cannot, however, explain where the range of different environments comes from. For that, many physicists consider some form of multiverse. The word describes several distinct ideas rather than one single theory. In one version, cosmic inflation continues in distant regions, producing many expanding domains with different physical conditions. In another, a deeper theory contains an enormous landscape of possible vacuum states, each giving rise to different particles, forces, or constants. Some regions may never form atoms, some may form only simple atoms, others may permit complex nuclei, chemistry, stars, and observers. In such a setting, The existence of atomic matter is not typical everywhere, but it is typical within the small subset of places where complex observers can emerge. The multiverse can turn apparent fine-tuning into a selection effect. If enough domains realize enough possibilities, then some will naturally possess the balances required for atoms. Observers will arise only in those domains and will find their local laws strangely suitable. This does not prove the multiverse. The idea becomes scientifically valuable only when connected to testable theories and observable consequences. Distant domains may lie permanently beyond direct contact. Measures over infinite collections create difficult mathematical problems. Different versions of inflation or high-energy theory produce different predictions. It is possible for multiverse reasoning to explain too much too easily if every observation is assigned to some unseen region. A useful scientific explanation must constrain possibilities rather than merely accommodate them. Research therefore continues on whether multiverse models yield distinctive statistical patterns, whether they follow naturally from independently supported theories, and whether their assumptions can be tested indirectly. Another proposed answer places intention behind the physical balances. Some interpret the suitability of the universe for atoms and life as evidence of design. This is a philosophical or theological conclusion rather than a result established by physics. Science can measure constants, model alternative conditions, and examine natural mechanisms that might select among possibilities. It cannot test an unspecified designer whose choices are compatible with any outcome. The design interpretation may hold meaning within broader worldviews, but it does not currently provide a predictive physical model. The scientific mystery remains even when philosophical answers are considered. The laws still need to be described, their relations measured, and their consequences understood. Perhaps the deepest difficulty lies in the form of the question itself. Asking why atoms exist may seek several different kinds of answer at once. One answer describes mechanism forces and quantum states bind particles into stable structures. Another describes history, expansion, and cooling allow those structures to form. Another seeks mathematical necessity. Deeper laws might fix the relevant constants. Another seeks probability among possible universes. Atomic ones may be rare or common. Another seeks purpose, a category that physics may not be equipped to address. Confusion appears when one kind of answer is mistaken for another. A complete account of atomic formation does not automatically explain why the laws permit it. A selection effect does not create the universes from which selection occurs. A deeper theory may explain values without explaining why that theory exists. Each answer can move the boundary of mystery without removing it. What remains certain is that atoms are not trivial. They arise from a long chain of physical conditions extending from quantum fields to cosmic expansion. Matter survives an early imbalance with antimatter. Quarks confine into protons and neutrons. Nuclear forces create light nuclei. Electrons wait through hundreds of thousands of years of heat before settling into bound states. Quantum rules prevent collapse. Stellar furnaces create heavier elements. Chemistry turns electron structure into molecules, worlds, and life. At every stage, stable patterns emerge from restless processes. The universe becomes capable of examining itself through arrangements of the same atoms whose existence requires explanation. Whether those atoms are necessary, accidental, selected from a wider reality, or grounded in principles not yet discovered remains open. The mystery does not weaken the science that explains their behavior. It gives that science a farther horizon. Everything familiar is made of atoms because atoms are stable, abundant, and chemically versatile under the laws of this universe. Why the universe possesses laws of that kind is a question still waiting beyond the edge of the atomic world.